Hello everyone! So today we will be demonstrating our research, which is about equilibrium and Le Chatelier's principle, improving the quality of general chemistry education. My name is Alisha and this is Alexa. And so to first start off our presentation, we just want to demonstrate what exactly is equilibrium. Equilibrium is quite a difficult concept to understand just by saying words, so I'm going to have Alexa here do a little demo for you what it exactly is.
Okay, so I'm going to do a basic demonstration. If Alisha will hold this for me. We're going to imagine these red pieces right here are people standing in a hallway, and these yellow pieces are people standing in a classroom. If one person leaves the hallway, a person from the classroom has to go out and vice versa. They can keep doing this, and you can switch pieces. It doesn't matter who goes where, but as one leaves, the other one has to enter. And this will continue for an infinite amount of time. But if I were to add 5 more people into the hallway, rather than one leaving and one entering, it's going to continue to funnel into the classroom to try to balance out to its initial state. This is a very simple demonstration of what equilibrium is, and it's keeping balance in a reaction.
So first, I'd like to just go over our abstract. So what Alexa just demonstrated to you was equilibrium. Now, Le Chatelier's principle is a concept that deals with chemical equilibrium. Le Chatelier's principle basically states that if you have stress put on the products or reactant side of a reaction, then in order to relieve that stress, the reaction will proceed the opposite way. So for example, I have carbonic acid, which is H2CO3 on the left side here, which will disassociate to carbon dioxide and water. So for example, if I add too much in excess of carbonic acid, the reaction will go ahead and proceed towards the right because it wants to relieve that stress.
And this is the same thing I was demonstrating when the pieces filed into the hallway. They shifted to the other side to try to fill the classroom up more to find the balance again.
Now, it's important to realize that equilibrium means the forward rate of reaction and the reverse rate of reaction are equal. It does not mean that the amount of carbonic acid is equal to the amount of carbon dioxide and water. And so this is quite a common misconception among students, and there is no sufficient demonstration available to help them understand this. So we have conducted research to develop a demonstration that works consistently, clearly, and can be performed in a basic high school laboratory in an AP chemistry classroom, as well as a general chemistry classroom in college.
So to begin with our actual demonstration, there's a few things you need beforehand. We tried to keep things limited to what a general high school laboratory would have, so that way plenty of people can use the demonstration. You're going to need an unopened bottle of club soda, a bottle or a can. It needs to be stored in the fridge, and it's very important that it's a new bottle each time you start your experiment. You're going to need a magnetic stirrer, which is a plate that connects to a little magnet, and the magnet goes into your flask and it will stir the solution as you turn it on. You need a pressure sensor that connects and measures the pressure changes, which reports on your LabQuest device. You need a larger beaker, you need a smaller Erlenmeyer flask, and you need approximately 15 boiling stones.
Okay, so now we're going to go ahead and talk through a video with you where Alexa is doing the presentation. However, we have this procedure here written for you just for you to look at. This procedure would most likely be written, given to the students to follow.
And if you do want to replicate the experiment, you need to make sure and follow the procedure exactly, because everything in it is very important and very precise. So if you'll just refer to the video here, as you can see, I'm going to start off by adding 50 milliliters of carbonated water.
And Alexa right here is just putting on the pressure sensor, the pressure stopper, to make sure that no excess gas is being entered. And she's putting it here in a water bath to make sure the temperature stays constant.
And I'm going to go ahead and place it on the magnetic stirrer. As you can see, you want to make sure that all of the tubes and it's fitted very tightly and no excess air is escaping. I'm going to go ahead and attach the syringe and pull approximately 90 milliliters of air. You're just trying to get the excess air out of the flask before you start so you can establish an initial equilibrium line.
Yes, so initially we pull out 90 mils of excess air that has entered the system just by opening the soda bottle and whatnot. And so here we are still pulling out the excess air.
And once you've pulled out the excess air, you're going to go ahead and begin your LabQuest. You're going to start your stirring rod to a medium speed of about 3 on our system. You might have to hold the flask down in the ice bath just because you are trying to get through 2 different glass containers, so it's difficult for the stirring rod to make contact if you're not holding it down. And as you can see, we're going to try to wait about a minute to get in a solid equilibrium line to begin.
And so here, Alexa's pulling out the carbon dioxide that has formed around 60 milliliters. Here I'm closing the valve. And so she's going to make sure to remove that excess air. And if you look over, which we'll pan over to the lab quest, you can see that huge dip in the graph.
And that dip results as you pull the air out of the system, you're creating stress. And so Le Chatelier's principle says that it's going to try to reach your initial equilibrium line to get back to where you started to balance out the stress in the system.
Now this can additionally be used if we want to put air into the system. So here she just pulled in air into the syringe, and now she's putting air into the system, and you can see on the graph that it went up and up on the graph, and it's going to try to reach equilibrium once again.
And you can do this multiple times, however it works. The biggest thing is you want to give it time to balance out in the beginning and to get back to that equilibrium line. And if you'll go ahead and refer to these graphs, this is what we're looking for. So the graph on the left is one that we achieved multiple times, and it's a perfect demonstration of equilibrium. As you can see, you have a strong starting line, and when you pull air and get back to it, it goes to the middle every single time. But because science doesn't always like to work with you, it's hard to get this graph every single time you perform this experiment. So what we aim for with our methods is the graph on the right. Even though it doesn't get back to the middle equilibrium line, you can see that it's making a strong effort to do so, and this will demonstrate to classes what equilibrium actually is.
Now, some of the challenges we faced are keeping other variables constant, such as temperature and volume. So initially, we did not have the magnetic stir or an ice bath. And once we put the magnetic stir in, we realized that the temperature inside the system was getting too hot. So that's why we put in a water bath in order to keep that temperature constant. And the volume was also an issue because as pressure is changing, volume is inversely changing. So that's why we had to keep removing air to make sure the system is at equilibrium. Also, we needed to establish initial equilibrium. Establishing initial equilibrium does take quite a lot of time, so that's why we limited to around 30 seconds to a minute just to establish that line. Like I said, there were quite a bit of time restraints, and the equipment we wanted to make sure that a basic high school laboratory would have access to.
So there's a bunch of different things we tried when we were first starting with this demonstration. One, we needed something that facilitated the formation of CO2. We tried various things: marbles, rocks, sand, and boiling stones. They're all relatively easy to obtain, but we found that boiling stones worked the best.
For liquid, we also tried various amounts of liquid, water plus baking soda, Dr. Pepper, and soda and vinegar, but we found that the most cost-effective and the most reliable was soda water.
And we altered other variations. We tried ice bath, we tried using cold liquid, we tried using everything at room temperature, we added a stirring rod, and we did all of these separate at first before we decided what worked best together to speed up the reaction.
So what actually worked? Well, the boiling stones worked because they allowed for pockets of carbon dioxide to form more quickly, so that allowed for us to do the demonstration more quickly. The club soda obviously worked because it was cost effective, and it also just allowed easier access for everyone. The ice bath also worked, like I said before, to keep the temperature constant due to the magnetic stir. And the magnetic stir also just allowed for everything to kind of bond together.
Well, this may not be clicking for everyone. You can see that it's a very abstract concept students have. We have on good accounts that kids never expect what to happen actually happens, because if something starts to go down, you assume it's just going to continue going down. It's really odd for it to actually go back up to equilibrium, and that's why we need this demonstration in classrooms.
All right, thank you so much for listening to our demonstration, and if you have any questions, please contact us at our emails as listed.
Thank you so much for watching, guys.
All right, bye.